Welcome to today's Explainer. We're going to transform your standard geometry worksheet into a dynamic, step-by-step masterclass on the properties of special quadrilaterals. I am absolutely thrilled you're here. Grab your notebooks and a good pencil because we're going to map out our solutions line by line, just like we're writing on fresh notebook paper. We'll emphasize exactly how to think through these geometry puzzles. Let's get right into it. Take a look at this beautifully complex machine of angular measure. All those gears and protractors perfectly represent what geometry really is, a totally interconnected system of rules. Our goal today is to decode the precise rules that govern some of the most fascinating geometric shapes, turning all those moving parts into simple, crystal-clear logic that you can use to solve literally any problem.
Here is our agenda for today. First, the rectangle. Second, the rhombus. Third, the square. Fourth, parallelogram transformations. And finally, a final practice challenge.
Section 1. The rectangle. Let's dive right into our very first shape.
So visually, we all know what a rectangle looks like, right? You've been drawing them since kindergarten. But in the strict world of geometry, a rectangle actually has a very specific definition. It's officially defined as a parallelogram that has exactly one 90-degree right angle. Just one. But as you'll see, that single right angle acts like a domino, triggering a whole set of new rules.
The absolutely crucial point here is that because it's a special type of parallelogram, the rectangle automatically inherits all of those base rules, things like opposite sides being equal and parallel. But it adds its own unique features to the mix. That one right angle actually forces all four internal angles to become exactly 90 degrees. Plus, the diagonals, those lines stretching from corner to opposite corner, become perfectly equal in length. So line AC is exactly the same length as line BD.
This is a common exam question, so let's work through it step by step on our digital notebook. We're told the measure of angle A is 4x minus 18 degrees, and we need to find x. Watch closely as we write this out line by line. Since we just established that every angle in a rectangle is exactly 90 degrees, we know angle A must equal 90. Step 1, we write out the equation. 4x minus 18 equals 90. Step 2, we need to isolate x, so we add 18 to both sides. 4x equals 90 plus 18. For step 3, that gives us 4x equals 108. And finally, step 4, we divide by 4, giving us x equals 27. Notice how setting up that underlying geometry rule right at the beginning makes the algebra an absolute breeze.
Okay, I want you to pause here for just a second. Try to answer this quick knowledge check based on what we just learned. If a basic parallelogram suddenly has diagonals that are perfectly equal in length, what does it become? If you said rectangle, you are absolutely correct. That is the defining upgrade from a standard parallelogram. Moving on to Section 2, the rhombus. Let's see how our rules continue to build.
Just like the rectangle, a rhombus is born directly from a standard parallelogram. But instead of changing the angles, a rhombus is defined as a parallelogram where two adjacent sides, meaning sides right next to each other, are equal in length. And just like before, this one simple change forces a really cool chain reaction throughout the entire shape. That chain reaction means that if two adjacent sides are equal, suddenly all four sides become equal in length. But here's the real trick you need to remember for your tests. Pay close attention to the diagonals. In a rhombus, the diagonals cross each other at perfect 90-degree right angles. They are perpendicular. And not only that, but as they cross the corners, they slice those interior angles perfectly in half. They bisect them.
Let's look at another example. We have a rhombus where side AD is 6x minus 4 and side DC is 5x plus 1. Our goal is to find the actual length of side BC. Step 1, because it's a rhombus, we know all sides are equal. So we set AD equal to DC. 6x minus 4 equals 5x plus 1. Step 2, we move the x's to one side and the regular numbers to the other. 6x minus 5x equals 4 plus 1. Step 3 gives us x equals 5. Now be careful here. Many students make a mistake in this step and just stop at x equals 5, thinking they're totally done. But the question asks for the physical length of side BC. So step 4, we have to plug x back in. Let's use side AD. 6 times 5 is 30. 30 minus 4 is 26. Since all sides in a rhombus are exactly the same, if AD is 26 centimeters, then side BC is also exactly 26 centimeters. Always reread the question before moving on.
Section 3, the square.
Now,
What happens if we take the right angles from the rectangle and the equal sides from the rhombus and smash all those rules together?
We get the square. It is the absolute VIP, the ultimate quadrilateral. It perfectly balances all the rules we've talked about so far into one incredibly symmetric, perfect shape.
You can think of the square as being a bit greedy. It takes every single property we've discussed today. It has the equal opposite sides of a parallelogram, it has the perfect 90-degree angles and equal diagonals of a rectangle, and it has the 4 equal sides, perpendicular diagonals, and bisected corner angles of a rhombus. If a rule applies to any of those shapes, it automatically applies to the square. It's the whole shebang.
Let's see a quick trick on how shapes actually upgrade. The question here asks, what value of x forces a standard rectangle to become a square, given side AB is 3x minus 4 and side AD is 2x minus 1? Step 1. We know a rectangle already has 90-degree angles. To upgrade it to a square, it just needs its adjacent sides to be equal in length. So AB must equal AD. Step 2. Let's write it out on our notebook. 3x minus 4 equals 2x minus 1. Step 3. Group the terms. 3x minus 2x equals 4 minus 1. In step 4, we easily find that x equals 3. By finding this specific value, we've locked the rectangle's sides into perfect equality, transforming it completely into a square.
Section 4, Parallelogram Transformations. To make sure this really sticks, let's quickly summarize exactly how a basic slanted parallelogram transforms into these special shapes.
This is all about the conditions required for an upgrade, and this table brilliantly illustrates our building blocks. Look closely here. If you have a parallelogram, you can pull 2 different levers to change it. If you give it just one right angle, or if you force its diagonals to be equal, it snaps into a rectangle. If instead you make 2 adjacent sides equal, or force the diagonals to cross at 90 degrees, it transforms into a rhombus. And the ultimate transformation? If a shape fulfills both the rectangle conditions and the rhombus conditions at the same time, it becomes a square. Memorizing this table is absolutely the key to unlocking almost every quadrilateral geometry problem you're going to face.
Section 5, Final Practice Challenge. You've mastered the rules, you've seen the step-by-step logic, so now it is time to put your skills to the test.
We're pulling this directly from your classwork packet. Take a look at this fascinating hybrid shape. We have square ABCD acting as the foundation on the bottom, and sitting directly on top of it, sharing that top line, is a triangle marked with 60-degree angles. There's an unknown angle marked X right at the hinge where the triangle meets the square.
We've learned exactly how parallelograms upgrade into rectangles, rhombuses, and squares. Now grab a clean sheet of notebook paper, draw this figure out, and write down your steps just like we did in our masterclass today. Ask yourself, what do I know about the corner angles of a square and this 60-degree triangle? How will you connect the dots to prove the exact value of x? You've got this. And once you master this challenge, you have to wonder, what other hidden shapes are out there waiting to be unlocked? Good luck, and keep thinking geometrically.